Okay, the next lesson we're going to talk about here is dilation, scale factor, similar shapes, and finding the lengths of sides of proportional figures. And so this is not related at all to volume, but it is something, since we're at the end of the school year, and I want you to be familiar with this, it is something that I assigned. So I'm going to give a quick lesson on it. So dilation. A dilation is an increase, we call it enlarging, or decrease, reducing in the size of a shape. You can think of when you print out a paper and put 200 in the print scale, that makes it bigger, and if you put 50% there, that makes it smaller, and that's the concept of scale factor. And so a scale, that's the concept of dilation also. And so a scale factor is the multiplier that enlarges. So 200%, of course, is greater than 1. That's 2, so that would make it bigger. And 0.5 or 1/2 is 50%, and that would make it smaller. And so here's our original shape. And so if we multiply this side by a scale factor of 2, it becomes 4. And this side times a scale factor of 2 becomes 8. And so we see that these sides got twice as big. And here, if we take the original shape and we multiply it by a scale factor of 0.5, the width here is 1/2 of 2, and the length is 2/2 of 4. And so these sides are proportional, and these shapes are what we call similar. They're the same shape, but different sizes. And I'll go over that vocabulary later. But anyway, some observations. The lengths of the sides are proportional. In other words, they are multiplied by the same number. Of course, we multiplied by the same number, so of course they're the same. They're proportional. But the areas are not proportional. I didn't talk about the areas, but let's look at the area. 4 times 2 is 8. 4 times 8 is 32. Well, we multiplied by 2, but the area got 4 times bigger. And so here, when we multiplied by 1/2, the area of 8 went from 8 to 2. It's 1/4 of the area. And so be very careful, because the areas are not proportional. And so this is an example of well, it's an example of why I always buy an extra large pizza, because it's the best. It's a lot more pizza. And there was a pizza company that, and a carpet company that I heard of years ago, that they doubled the size of the pizza, and of course they doubled the price. They doubled it was a 5-inch radius pizza, and we're going to give you a 10-inch pizza for just double the price, okay? And so what happens, though, is it's 4 times the area, so they actually hurt their profits by a significant amount. They almost went out of business. The same thing I heard with carpeting. When you double the size of a room, the sides of the size of a room, you actually quadruple the area. So remember that if you ever do an estimate for carpeting or tile, that it's not proportional. Okay. Determining the scale factor. A scale factor is a multiplier, and if it's greater than 1, of course, you can imagine that a number will get bigger. If it's exactly 1, and it won't change at all, but if it's between 0 and 1, we call those fractions and decimals, the sides will get smaller. So how do we find the scale factor, however? The scale factor is made by a ratio of the new length to the over the original length. And you should also observe if the figure is getting larger or smaller. Of course, triangles and shapes don't come with the word new and original on them, so sometimes you just have to come with that information. And this fraction bar here is misplaced. This should say scale factor equals new over original length. So I'm not going to change that now, but there should be a fraction bar there. And so what is the scale factor in this example? Well, we went from 4 to 6, and down here this went from 2 to 3. So the new over original is 3 to 2. Oh, here it is, 2 to 3. And so you would think it's 2 over 3. No, it's 3 over 2. that fraction right there, if we're going to make it a scale factor getting bigger, it has to be more than 1. And so 6 over 4. And these are equivalent fractions, and 3/2 or 6/4 is both equal to 1.5. So the scale factor here, 1.5 times 2 is 6. 1.5 times 2 is 3. My mistake. 1.5 times 4 is 6. And so that's the scale factor. We have to be corresponding sides. 3 over 2, 6 over 4. Okay, so what is the scale factor here? Well, first let's look at this. Is this triangle are the sides getting bigger or smaller? And I would say it's getting smaller. Now, we just drew this by ourselves, so it may not look to be similar in shape, but it is the same shape. So, observe that the figure got smaller. So we know that our scale factor has to be less than 1. And so that will help me. Is it 5 over 2 or is it 2 over 5? So it's 2 over 5 will make a fraction less than 1. 5 over 2 is the wrong one. So if we're going to multiply going left to right, our scale factor is 0.4. So now a new thing. How do we find these missing lengths? If these are in fact similar triangles, how do we find these missing lengths? Well, we multiply by 0.4 and we got 1.6, and we multiply that by 0.4 and we get 1.2. And so that's how you use a scale factor to find the missing lengths, or the missing lengths of the sides of a triangle, or any figure for that matter. Okay, next. What are the missing lengths of the sides here? Well, here we have no new or original. We have 5 and 8 and X and 5 and 4 and Y, and I color-coded them. And notice that they are not in the same orientation. This triangle has been flipped over. But I can still determine the corresponding sides are 5 and 8. The yellow sides are the only sides that we have the numbers for. So we could either use a scale factor of 5 over 8 or 8 over 5. And it doesn't really matter, but in my preference is I like to think of this as getting bigger. So I'm going to make a scale factor where 8 over 5 is greater than 1. That's making it bigger. But if we go from this direction to this direction, we're not going to multiply by the same scale factor. We could divide by 1.6, or we could use 5/8 going right to left. So you see down here I've done both scale factors, but I like going from left to right, and I would probably end up dividing this by 1.6 to get that one. So anyway, our scale factor is 8/5, and that's 1.6. So if I multiply 4 going from left to right, if I multiply 4 by 1.6, I get the length Y here, that is 6.4 meters, and it is bigger. And the number I got is bigger than 4, and that's important that I check that. And then going from here to here, from X to 5, well, I'm going from bigger to smaller. So again, I would use the 1.6, and instead of multiplying by 1.6, I would divide by 6. That's what I would do, and I get 3.75. But you could certainly just use flip the reciprocal of that scale factor, flip it over, and you'd get 0.625 as an equivalent fraction, and that is 3.75. So either way it works, and that is smaller than 5, and that is smaller than 5 also. So there we go. That's how you find the missing lengths, and you could use two scale factors, going from left to right or from right to left. Be careful and always check as the number makes sense, because if for example, if this number were 7, well, I can tell that this is the bigger triangle, so that shouldn't be 7, that should be less than 5. And conversely, if this number here is 4 and I got 3 here, then I know that that isn't 3 because this is supposed to be bigger than 4. So be careful of that as a check. Okay, and so in summary here, similar figures are found by using a dilation. And so the dilation is a multiplying by a scale factor. And so you get the same shape but different sizes. Okay, they're the same shape but different sizes. The corresponding side lengths are proportional. Okay, that's how we could write a proportion or two equivalent fractions. I like multiplying by the scale factor. The areas, remember, are not proportional. Be careful of that. Since the figures are the same shape, all of the corresponding angles in the figure are the same measure. Okay, that makes sense. If they're the same shape, then the angles are the same measure. And then congruent figures, which we didn't talk about this time, but we did talk about in class about rigid transformations. That comes before dilations. And there are three types of rigid transformations, but they give you congruent figures, exactly the same size and shape. And well, how are they transformed? Well, they're either slid, we call that translated, or flipped over, we call that reflected, or turned somehow, we call that rotated. But the congruent figures are still the same size and shape, and so the corresponding sides are exactly the same length, and the corresponding angles are the same measure also, just like the similar figures, because the figures are what we call congruent. They're the same size and shape. They've just been changed a little bit. So that's our lesson for today. Thank you so much, and have a great day, and I'll hope to see you soon.